Okay, so before we dive into some live demonstration of RISA-3D, I want to take a moment to review the various diaphragm options that exist within our workflow. So there's three main options. The first is a rigid diaphragm. Next, we have a semi-rigid diaphragm. And then finally, a flexible diaphragm. Now, diaphragms are what the software is going to use to distribute lateral loads, be them wind or seismic, to elements in the model, whether they be shear walls or moment frames or brace frames, which are going to resist these loads. Now, the type of diaphragm that you use makes a huge difference on how you get the load transferred into that lateral resisting system. So let's go ahead and use this really simple example to evaluate the differences between kind of diaphragm action and how load is going to get distributed. So in this case, we have a simple diaphragm. We also have some shear walls. You can see those shear walls are of equal length and equal thickness, so basically equal stiffness. And we also have a load that's being applied along one edge here. So we have the wind and seismic load. So if I go ahead, we can first look at the rigid diaphragm. So rigid diaphragms, which we're using in this case on all the lower floors, assume that everything on a given level is rigidly attached. So there's no distribution of axial forces between the diaphragm plane. And actually the load applied is applied directly to the diaphragm and distributes based on the stiffness of whatever is attached to the diaphragm. So in this example, we have all three shear walls, again, that they're the same length and the same thickness, and therefore they receive all the same proportion of the load applied to the diaphragm. So in this case, a third of the load. Also, the diaphragm, you can see, is going to move kind of together, right? So we're going to have all this, because of this rigid connection, we're going to have this deflection and this lateral movement that is the same kind of everywhere. So in our model, we're calling our composite floors on the lower levels rigid. Now the next option, obviously, is a flexible diaphragm. Now these are the complete opposite from a rigid diaphragm because they have zero stiffness. So when we say, a flexible diaphragm, we truly mean that. They have zero stiffness. So load is distributed based on the tributary area or width, like a hand calculation method, regardless of the stiffness of the lateral resisting elements. So in this example, we can see that half the load goes to the middle wall and 1/4 of the load goes to each end. Again, this is based on that tributary area or tributary width based on the load applied to that side. So one thing to think about when you're using flexible diaphragms is that a flexible diaphragm, because in our case it has zero stiffness, there's not going to be any rigidity that it's providing to the top of a wall, say. So when you're using like a wood wall, they may have the tendency to simply kind of fall over due to the minimal stiffness in the wall and no kind of stiffness at that maybe top diaphragm. So that's why adding things like straps to tie the walls together at the floor levels is so important. Now in our situation, we're using a metal deck at the roof level, which is our flexible diaphragm, but we are using concrete shear walls. And these obviously have stiffness both in and out of plane. So we're not really worried about those walls just kind of falling over due to that flexible diaphragm. The third option here is a semi-rigid diaphragm. So the semi-rigid diaphragm, we try to model the accurate stiffness, so the actual stiffness in the model. And so you can see here that we're actually creating a sub-mesh of the actual floor plate. And based on how things are connected to each other, we're going to get this more accurate stiffness. So using plates, this stiffness is based on the actual properties of the material and the thickness. So back in RISA floor, we had to define how much of that 4-inch composite slab we were going to use to calculate the stiffness of the semi-rigid diaphragm. In this case, we choose to use 2 inches of the concrete, and that's the 2 inches that's solid above the composite decking, so that we can use that 2 inches, that kind of solid 2 inches, to calculate the properties of the semi-rigid diaphragm. Obviously, because this is going to be a plate mesh, this is going to be the most accurate portrayal of how load is transferred, but obviously it leads to a much larger solution time, much larger model, much more complex, and obviously the results are much more difficult, not to interpret, but to kind of compare to traditional hand calc methods or even a traditional kind of rigid diaphragm analysis where you kind of understand how everything's stiffness is working together. Obviously, this is where the power of a computer software really comes into play when you want to do a semi-rigid analysis. Now let's go ahead and take a look at the load application on each level. So when we have a rigid diaphragm, that load application is applied directly to the center of a model. So basically this point at the center of rigidity then transfers the load via internal rigid links to all of the connecting elements on that level. So all nodes are rigidly connected together. So in this case, the rigid diaphragms can be created independently in RISA-3D, so without first having to tie the model into RISA-Floor, which we've done previously. Although their definition then is simply based on a selected node, which is then rigidly connected to every other node in the same plane as that node. So we don't have to use rigid diaphragms with RISA-Floor. We can do them separately just in RISA-3D, but in this case, we chose to set that in RISA-Floor and then transfer that over into RISA-3D. Now, the next application obviously is a flexible diaphragm. So for flexible diaphragms, loads are applied in the center of the model in both directions prior to the solution. But then during the solution, something else happens. So during the solution, the point loads are broken down and applied to elements based on the tributary area. And so we see these as transient distributed loads. And we'll go ahead and take a look at that in our RISA-3D model. And so these transient distributed loads are simply a reminder of how the overall load, whether it's a point load or an area load, is broken down and distributed during the solution in RISA-3D. So it's really just another kind of check to see, okay, I had this one point load, and then that point load got broken down into these points, and so they can see maybe the chord forces or these forces and how this load is distributed. So it allows you to kind of check and validate these results much more easily. The next option obviously is a semi-rigid diaphragm. In this case, we're going to look at a semi-rigid diaphragm wind loading. And so when looking at this wind loading, wind loads are applied to the edge of a diaphragm in the direction of the applied load. So in this example, we have a plus X, we have a negative X, we have a plus Z, we have a negative Z. So all these loads come into play when building lateral load combinations in RISA-3D. So these loads that applied on the edge are going to be kind of dragged through the semi-rigid diaphragm, and then obviously different elements based on different stiffnesses and different connectivity to the semi-rigid diaphragm are going to get different load application. Now, when we're looking at a seismic or earthquake loads, the seismic loads are applied based on the location of masses at a specific floor level. So in this case, there are loads applied at the columns, at the walls, and then wherever we have the superimposed loads applied to the structure. So basically where else mass exists. So basically we have got some mass for the floor, at the top of the columns, at the top of the walls, and that's the location where all those nodes or all those loads are going to be applied. So now that we've looked at some basic examples, let's go ahead and talk about kind of our example specifically. So for seismic loading, we've chosen kind of a middle of the road city as far as seismic activity. Not really the highest, like in California, but not obviously the lowest, maybe somewhere on the East Coast. But Oklahoma City has a pretty decent amount of seismic activity due to some of the stuff that's going on there. And so we can see these are the kind of the equations. These are the information that we're going to use based on the USGS that we're going to use to create the seismic load using our 3D seismic generator in RISA-3D. Now, one comment that we want to make here, and Debbie mentioned this a little bit, one comment we want to make is about the seismic weight or the seismic mass of the structure. So before we go ahead and run the lateral load generators, we need to make sure that we've kind of evaluated this here in RISA-Floor. And so in RISA-Floor, we have the option to choose the element self-weights that are included in the mass. So we can choose whether the gravity members or the lateral members or the decks or the slabs, whether those self-weights are going to be included in the calculation of our mass. It's also important to remember that back in RISA-Floor that we assigned what's called a dyne load, right? A dynamic load that's going to be used from the uniform area loads spreadsheet as an applied load or applied mass to the floor levels for the calculation of the overall mass of the structure. So in this case, we can see that in some cases it's going to match directly to our post-composite dead load, so our overall dead load. But in some cases you may not want that, right? So we've actually reduced it for maybe a storage area, or we've reduced it for maybe the roof or something like that. But that's the load, that's based on the area load that you apply to the structure. That's the load that's going to be taken into account when you use your seismic weight, when it's calculating the overall seismic weight of the structure. So now that we've gone through some of the basics and some of the theory behind diaphragms and how we're going to use diaphragms in RISA, let's go ahead and switch into RISA-Floor. So I'm going to jump into my RISA-Floor model, obviously the same exact RISA-Floor model that Debbie was working in. And so I've got the analysis already run. We did the design, the gravity design for our case is done. We now need to make that transfer using the director to RISA-3D. So I'm going to come up here to the director. I'm going to choose RISA-3D. So the first thing that pops up here is our load generators. So we have the wind load generator, and so we can choose the parameters of our wind load generation. So we'll choose the code, we can choose the wind speed. A lot of this is set based on what we use in what we're going to use in Oklahoma. And so in this case, I'm going to say ASC 716, so we'll use the most recent code. We use 120 miles per hour. If we change anything here, we can go ahead and click this Calc Loads button, and we're going to actually get a calculation based on what's happening here. And so this would update, and so you can see those changes to see, yeah, that's about what I want. So it's a good first kind of sanity check when you're doing this kind of analysis. So we can see all the floor level results. We can see also all the loads applied. Additionally, in this table here with the loads applied, you can see we have that additional parapet. So Debbie added that parapet level, and so we can see actually the combination of that parapet and the main wind force resisting system loads. And so from the parapet here, we've got these different parapet zones based on the heights that we applied, and we're getting an additional force that's going to be added into the total for that floor 9 here. And we can go ahead and then look at that in more detail when we look at the results that are going to be transferred into RISA-3D. So if we go ahead and just click OK, the next thing we're presented with is the seismic load generation. Obviously, we've got our seismic code here set, so I'm going to stick with the same ASCE 716. Now we do want to change some of the other factors here. So maybe we want to keep the risk category the same, so that's fine. Let's change the SD1 based on that criteria that we saw in our PowerPoint presentation based on the location of Oklahoma City. So I'm going to go ahead and set this as 0.052. Let's go ahead and set the SDS as 0.177. We can set the S1 factor as 0.077. I'm going to also go ahead and set my R factor. I'm going to make this 3.5. And for me, this is going to be kind of a choice, kind of an engineering judgment choice. But for a mixed shear wall and ordinary braced frame system, I'm going to go ahead and choose to use an R value that's not quite R of 3, which is not detailed for seismic, but is maybe a little bit between the two. So I'm going to use that R value there. Now with those changes made, I can go ahead again and say calc loads, and these are going to, everything here is going to update. So again, this is a really great tool. If you wanted to include this in your output, you wanted to include this in your report, you'd be able to see this information to see exactly how the things were calculated. So here we can see, okay, the weight at each level, at the height of each level, what's the force that's going to be applied, and at what center of gravity in that floor is it going to be applied. And so we can see all this information. Additionally, we see the information with the eccentricities. And so we're going to have those eccentric loads applied based on those seismic conditions. And we'll go ahead and see those applied at various nodes through the model as we see it. Now, this information can also lastly be used to verify the weight of the structure and compare those against rough hand calculations. So again, kind of that first overall sanity check to make sure, okay, do I have the right mass? Do I have the right load applied? Am I seeing anything drastically different? You know, if we saw two floors that were generally the same layout and they had drastically different forces applied here, you know, in this case, you know, if we were looking at floor 2 or floor 3 and floor 4, you know, they have slightly different framing, but they have really close loads here. So the weight and the forces applied are pretty much the same. And so we can see, okay, yeah, we're starting to get the loads that we would expect. So I'm going to go ahead and click OK again here. Now, when this happens, we're going to generate all the loads and generate all the common information. Also, it's going to transfer all of the loads, obviously, into those transient loads from RISA floor into RISA-3D. It's automatically, for me, going to open up RISA-3D. So we're going to launch RISA-3D here. And then it's going to write the rest of the model. And so when we do that, we can see our model here. And so remember, because we set certain elements as lateral elements, those are the elements that come over in the model. And so we can see here all the lateral elements, all the elements that were defined as lateral. Now, for this particular example, I've already defined some of the brace frames, and we'll go ahead and define the rest of them in a minute here. But let's go ahead and look at the nodes. So we have a ton of nodes kind of floating in space. Those nodes are all what are being used for the application of wind and seismic loading. So let's go ahead the first time and turn on our diaphragms. So I can turn on our diaphragms here, and we can see kind of various different colors of diaphragms. If we look at this as in an ISO view, so we've got our rigid diaphragms denoted in purple. We've got our semi-rigid diaphragm here in green, or maybe this bluish color. And then finally, our flexible diaphragm is this brownish color at the top. So I'm going to go ahead and take a side view here, and I'm going to deselect everything and then only select like level 2. So I just want to see the results on level 2. So I'll go ahead and lock that level and show an ISO. And so in seeing this, we can then go ahead and turn on some results. So let's go ahead and turn on the visibility of results. And again, we can start to see these nodes being used for different load applications. So earthquake X, right? Let's choose basic load case, earthquake Z plus eccentricity. You know, maybe there's different wind loads here, right? We've got all these different options. And so we can see these loads applied on the structure. So these loads include all of those pre-generated partial loads and eccentric loads that are required by the code. So let's go ahead. I'm going to turn everything back on. So let's unlock everything and turn everything back on. And I'm going to go ahead and do the same thing. I'm going to get a side view, and let's just go ahead and deselect, and I want to select only the semi-rigid level here. So let's just select that semi-rigid level and lock everything again. And so when we do that, we can go ahead and see, I think we should be able to see our semi-rigid loads, right? So we have our semi-rigid loads then applied to the structure at that level. And remember, those semi-rigid loads, because we have a mesh, right, are going to be applied to the kind of the edge of it, rather than we're going to have this load applied at a central node in the system, because that load is going to be dragged through all of those connected mesh elements. Now, at any time, if you want to make a change to the seismic or the wind load application that you just created, you can go back into the insert dropdown, and you can go to insert wind or insert seismic load, and that'll launch you right back into the 3D wind load generation tool. Okay, in this case, I'm going to turn everything back on again. So let's go ahead and turn off our loads, and then we can toggle on the rendered view of the model. And so I'm going to turn off my diaphragms, and I'm just going to turn off some of my nodes here. So just kind of clean up the model a little bit here. So the first thing that we need to do is we need to complete the modeling, obviously. And so I've already created some braces. So those braces are based on a section set, right? And so we set up a section set for brace. So I defined the label here, the shape, the type. It's a vertical brace. Our design list is going to be based on a single angle design list, a material, and then I have a design rule for brace. So if we go ahead and also look at our member design rules, we can see in our brace design rule, we could set various different things, whether they're max depth or max width or maximum bending or shear, or we could set some deflection requirements. For these braces, I don't really need to set any requirements, or I'm not going to require anything in this particular case. I'm just going to kind of let the basics or the standards go. But what I do need to do is I do need to create the remainder of our braced members here. And so I'm going to go ahead and turn off the rendering here. And so we can see that we've got our braces. They're pinned at each end. And so we need to create them in these last few moment frames. So I'm going to go up to our graphical editing toolbar and open our draw new members. And so we're going to choose to assign based on a section set. So I'm going to choose brace here. I'm also going to choose that they're pinned at both ends. So we want to automatically be pinned at both ends. And then I'm going to click apply, and we want to draw point to point here. And so I'm just going to start drawing point to point. So node to node to node to node. If I want to go ahead and turn on my nodes here to see a little bit better, I can go ahead and do this. Now, one of the things that's important when I'm drawing my members here is we do want to draw kind of in the same configuration each and every time. So basically, I'm drawing from bottom to top every time. And that's really because we want the I and the J node, right, the start and the end of each member to kind of be the same. We don't want, in one case or in one frame, the starting node or the starting end of the member to be at the bottom, whereas in another frame, we've got the starting member node to be at the top, right? That's going to help us when we go ahead later and assign connections or assign other information to the ends of members. It also helps us when we review loads or results throughout a member to see exactly, when we're comparing them, exactly what's going on. The other thing to mention here is all of these kind of floating nodes, right? And because And really, they're not a problem. They're not, untied to a diaphragm. Essentially, they are the nodes that the software is creating automatically as the center of gravity or the eccentric load or the partial wind load combination or case that those loads are applied to. So if we would kind of cycle through all the loads that are applied from the wind and seismic generator at each and every level, we'd see a load applied to each one of those nodes. And so you don't need to delete those nodes. You don't need to try to get rid of them. They're going to be there, and they're going to be there to help you apply those loads to the structure. Okay, so now the next thing that I want to kind of take a quick look at after we've modeled all of this stuff here is we do need to look at the design tab of the members for kind of our assigning of unbraced length. So I'm going to go ahead and look at, let's just go ahead and double click on one of the beams here. And so if I go to the design tab, we can see that we have various unbraced lengths for strong axis, for weak axis, for top and bottom, and then for torsion or torque. And so various unbraced lengths, they exist when linked with a RISA floor model, and then therefore they're designed in a RISA floor model. And this is really the way things are being modeled in RISA-4 and then how they're being transferred into RISA-3D. So in this case, we can see that one of these, so the top here, is coming from RISA-4. And that's really because it knows the beam is part of a floor system. It's a composite beam, right? And it's basically assigned to a deck, and it's got a composite deck above it. And so its unbraced length for that particular case, it knows that top flange is like tied to that floor diaphragm. And so it's automatically going to set that. Now, you may, as a user, specify any length that you want. You could use the different segment commands. So you could type in, segment here to say, hey, I want you automatically to break my unbraced length at any time a beam frames into that. So that's really good for like a girder or something like that. If nothing is specified, then RISA is going to use the default member length. And one of the things that I like to mention here is that other softwares maybe do other things with unbraced length. We are of the opinion that we want you to have some input. You want you to be able to define the unbraced length because it has such a large impact on how your steel or how your concrete is going to get defined or designed. And so you want to have your hands on it. And so obviously you could define it in here, or obviously we can come into our member spreadsheet, into our hot roll tab, and you can go ahead and really make some bulk changes to a variety of members or a mass of members at the same time to really quickly and easily make those changes to those unbraced lines. So now that we have our loads that are brought into the system, right, we've looked at some of the loads, whether it's our rigid diaphragm loads or our dead loads on the structure, right? All of these loads are tracked in so that we can see exactly what's going on. Now that we have all these loads applied, we can go ahead and set up our load combinations. So I'm going to go ahead and click on the load combinations button to open the load combinations spreadsheet here. And we want to create load combinations using the generator. Now we could create them from scratch again if we wanted to, but using the generator based on this code that you're using is going to make your design just that much more efficient. So we're going to go ahead and click on the generator. Now in this particular case, I'm not going to go ahead and create any gravity loads because we did the gravity design in RISA-4. Obviously we could create that if we're going to go ahead and evaluate and look at all this stuff, but for this example, I just want to focus on our wind and seismic loading. And so I'm going to click on the wind tab. And we can choose our region, United States. We can choose our code we're going to use. So let's choose an IBC ASD code. I'm also going to choose the options here. So I'm going to choose to use wind in the X and the Z direction with eccentricity and with quartering, right? So we want really all of the different types of load combinations to be created here. We can also choose that we want to generate the semi-rigid diaphragm loads because we have a semi-rigid diaphragm, so that makes sense. We could choose other wind loads and notional loads, but in this case, we'll stick to these here. And I'm going to go ahead and click Generate. Now, the next thing we can do here is go ahead and switch our tab to Seismic. So we'll go back to Seismic here. And again, the same thing. We're going to use the IBC 2018 ASD. And again, I'm going to go ahead and use X and Z with eccentricity. So that's going to give us a good load. But before I do that, one thing that I almost forgot here is I'm going to close out of this and I need to go into my global settings and I need to choose our seismic tab because there are some things within these seismic load combinations, namely the omega factor, the CD factor, and the rho factor that are important, right? We have to set those redundancy factors and those CD factors in order to properly calculate our load combinations. And so in this case, we're going to set our omega here for X and Z. 2 is fine. Our CD factor, that's going to be the same as our R factor in this case, so 3.5 works. And then since we're going to choose to have incorporate the redundancy factor, we're going to choose that 1.3 factor here. So this is set up exactly as we want it to be. So I'll click OK. Now I'm going to go back to the generator. We're back on the seismic tab. And I'm going to go ahead and generate the combinations with overstrength and redundancy. So let's say X and Z with eccentricity, X and Z with eccentricity. We'll include the redundancy. And we'll go ahead and include the vertical component. And then maybe we'll include the non-orthogonal if we wanted to. Maybe we don't have to. In this case, I'm going to choose to not include the non-orthogonal cases here. So that's good. We can go ahead and generate again. So if we close that out, we should see that we've got, in this case now, 80 load combinations to generate. Now, I'm going to go ahead and generate some additional combinations because we need additional combinations for LRFD design, right? So we have some concrete members, specifically these concrete shear walls. We can't do ASD design with that. So we need to go ahead and switch this to our strength level design. So let's choose our 2016 strength level. That's fine. Again, we'll choose the wind, generate that, switch back to the seismic, that same thing, generate that, click close. So now we have, let's see, we have 159 combinations. Now, obviously, it probably doesn't make sense for us to generate 159 combinations. So we can go ahead and turn on and off some of these different combinations. But before we do that, the first thing we need to do is we need to enable P delta on all of these combinations. Because P delta is a requirement for both concrete and for steel, we need to make sure that all of our combinations, whether concrete or steel, whether strength or ASD, has P delta enabled. So to do that really quickly, I'm going to go ahead and select the column. I'm going to right click and choose fill block, and I'm just going to type Y for yes in there and then hit enter. So we're going to get all of our combinations have P delta enabled. So that's really simple, pretty easy. The other thing here is you can see that we have a tab for combinations and a tab for design. And so in the design tab, that's basically saying, okay, for a specific material, what combinations are we going to use to design that particular material? So for instance, if we don't want to use, these first listed combinations are our ASD combinations. If we don't want to use ASD combinations for concrete, right, we can go ahead and disable those combinations. So if I wanted to select all of these combinations down to our strength level, right? So let's get down to the bottom here of strength. So that's where it stops. I can right click again and say fill block and leave this blank and click no. So we don't want that to be included. Same thing for down here with like steel, right? I don't want strength level design to be done for my hot rolled steel members. So I'm going to do the same thing, select all those, fill block, and click no. Now we could do that for the rest of our model here. We could disable different things for connections, whether we wanted to do ASD or LRFD for connections. So in this case, because connections is really the other thing that we'll worry about later, I'm going to go ahead and select to say, I don't want to do LRFD design for connections. I just want to do my ASD design. Additionally, we can choose which combinations are going to be used for serviceability and how that kind of duration factor is used. In this case, I'm going to keep those all the same as long as we've kind of set our steel and our concrete, which is what we have in our model. The next thing though I'm going to do is I'm going to come back here, and we don't want to solve all 159 combinations, right? That would take entirely too long. We'd get, we'd be here forever. And so I'm going to go ahead and select this entire thing again. I'm going to close it out so we can remove the solving for all of those. And I'm going to go ahead and set a specific number of combinations. So let's just choose, I'm going to choose this wind one, let's choose another wind one, in the X direction, the Z direction. Maybe let's choose one that has some of them together. So X and Z together, working together, with reduced factoring. So let's use that one. We can choose, a couple of the other ones. Let's go choose some of our earthquake ones. So those were all our wind ones here. Now we get to our earthquake combinations. So let's choose maybe 45, which is an earthquake combination, and 54 is an earthquake combination in the opposite direction. And then we need to choose some for concrete design. So let's get down here in the strength design and let's say, okay, let's choose, let's choose, 88. And so that has what, X direction and Z direction. And let's choose one that has kind of the opposite here. So let's choose 98. And then we need to get some seismic combinations. So let's go ahead and choose seismic for, 148. And then let's choose, so that has X direction specifically, and then let's choose something that has Z direction, so 137. So again, you could pick whatever combinations you want. You could run them all. Maybe if we were doing this, kind of in a full-blown model and we were going to do a full-blown analysis, we'd run them all and then we'd envelope everything and we kind of figure that out. But in this case, because we want to speed up this process a little bit, we're just going to go ahead and choose to run those 8 combinations. The next thing here is I'm going to go ahead and click the Solve button, and we are presented with some solution choices. So we can always solve a single load combination. So if we wanted to just solve one load combination and just kind of get going with that one combination, review some results with that one combination, we could do that. In this case, though, I'm going to solve a batch solution with the envelope. And really, that's the solution that I always choose. And so if I go ahead and click Solve here, we're going to start running our model. It's going to start running through the solution of each individual combination here, calculating P delta, running through the stiffness matrix, going through all the things, distributing load, kind of getting us all our results for each of those individual combinations. Now, the reason I run batch and envelope together is that batch is going to give you the individual load combination results. So if you wanted to review the results on combination 137, you could, but the envelope is going to say, hey, of all these combinations that you've looked at, as everything that you've evaluated, these are the worst case scenarios. And so we did that. We ran our analysis. We're going to have our results here. And really, we're going to get kind of the best of both worlds, I say. So we can evaluate individual combinations to see, why is this one failing, or why is this one giving me a problem in this case? But also, hey, if I want to just look at the worst case reactions, that's what I need the envelope for. Okay, so now that we have our results, one of the great things about this is we can go ahead and switch our kind of toggle here to see that we can actually look at results for load combinations, or look at kind of load applied for load combinations. So we can see, hey, in this particular load combination 1, let's even see what the first one is we ran, which is that, this is the load applied factored, right? So this is what's getting factored, this is what's getting applied on that particular level. We can also go ahead, and if I turn back on our diaphragms here, I'm going to go ahead and get a side view. So let's get our XY view here. Let's turn off everything, and I'm going to go ahead and view kind of the top here, but I also want to grab the walls here because I want to see that. So, and we can go ahead and look at, in ISO, look at some of the results on this particular wall. So again, if we go ahead and look at some of our transient loads, maybe we want to look at this, because this is a flexible diaphragm, and let's switch this to our wind load here. Our wind load, our transient loads are going to be calculated here. So we're going to get our transient load. So let's go ahead and look at, here we go. Our transient loads are calculated now based on that. So we can see here that this is basic load case 8. So this is the transient load that's coming from basic load case 8. So from basic load case 8 is our wind load in the X direction. And this is kind of that distribution like we saw in our PowerPoint presentation. This is the distribution taking this point load and breaking it down into the locations of what is going to resist it. So in this case, these line loads at the top of this shear wall here. Now, the first thing that I always like to do, so I'll turn off the loads here and let's get everything back on here. The first thing that I like to do is I like to look at my deflected shape. So let's turn off the nodes here and let's look at our deflected shape. So that's my first kind of sanity check. I just want to make sure that things make sense, right? And so in this case, if I had my frames that were really out of plane, or, I had this huge deflection over here and, this was really kind of tilted all the way over, we'd know pretty quickly that maybe I don't have a boundary condition correctly. Maybe I messed up something in the connection. Maybe I just missed, a node when I was modeling something. All of those things can be really easily kind of identified when you look at your deflected shape. And so we can also go ahead then and look at, in our results, our joint deflection spreadsheet. So when we look at our joint deflection spreadsheet, what I like to do again is kind of do a sort so that I can see the kind of the worst case. So for instance, in the X direction, this is kind of the direction that we're looking at now. I can go ahead and sort by absolute max, absolute min to see, okay, the worst case deflection in this X direction is at, a node at, kind of the 7th level, and it's just under a ½ inch. That's not unreasonable. That makes kind of sense to me. So, and that's in load combination 137. We can do the same thing for, let's say, the Z direction. We'll do the sort again, and again, say that, okay, we don't really have, too bad of deflections here. Probably the model is in pretty good shape. We didn't make any really big modeling errors. We don't have any really big issues here. The next thing we can do is we can evaluate the actual results here, right? So I'm going to go ahead and turn off that, and I'm going to turn again off our loads here. Let's also go ahead into our model here. And let's turn off our pinned ends. So let's go ahead and turn those pinned ends off. And we can go ahead and look at our design results. So again, if I look at my design results, the first thing I can see is that some of them are overstressed. So we just kind of modeled and kind of set what we wanted to. And a lot of these, obviously remember, a lot of these beams that are in the frames were initially designed for gravity. And so they've not yet been designed or optimized for the lateral loads in the system. And so again, I'm going to use the same kind of tool, the same sort tool, to see kind of what's failing. And so in this case, we've got a few of our beams that are in our moment frames, or in our brace frames, excuse me. And then we also have some of these angles. So some of these braces that are also failing. And so if we wanted to very quickly, let's go ahead, maybe I want to look at one of these braces. I can come up here real quick and look at the detailed report. So if I look at the detailed report, obviously, we can look at both the envelope and the individual load combinations that we ran. In this case, I'm looking at that envelope. We're seeing, okay, in load combination 54, I'm about 20% overstressed. And if we come down here, we can see, okay, it's not in shear, but it's in bending, right? We've got some bending issues in our braces. Now, in this particular case, I didn't set anything as as tension only. We didn't kind of remove the ability for them to not take compression, but maybe we could do that. Maybe that would have been a solution in this particular case. But we can also see, if you don't want to just evaluate this in a spreadsheet, we can see this graphically as well, right? So I'm going to go ahead and open up my model view options or my model display options, and I'm going to come over to my members and let's turn on the color coding, and I want to see the unity check. So apply here, and let's get the label on so we can see the label of the unity check as well. So now it's really easy to see, okay, we saw it in a table, kind of what was going on. Now it's very easy to see the members that are failing. The other thing that we can do here is we can select the result. So in this case, we're using that first combination. Let's choose to member envelope it so we can see, okay, worst case for all of these different members, here's what's failing, right? So here's our beams and our braces in a couple locations that are failing. So some of the braces at the bottom of the brace frames, those are the ones that are causing us issue. Now, if we wanted to, we could come over here into the suggested design, and RISA is actually going to suggest for us the design or the shape that we need to change to in order to, meet the controlling criteria. So in this case, in order to meet the strength criteria, or in order to meet a deflection criteria in the case of some of these beams. Now, you could go ahead and just say, hey, RISA, I trust you. You can do exactly what you're suggesting. And we'd come up here and we would just click, go ahead and replace current shapes with what we're suggesting. And it would basically replace those shapes, rerun the model, and then we'd have new unity checks and be able to evaluate that again. In this case, we're not going to do that. We're not going to take the time to do that. We could also disable some of these to say, you know what, even though this is saying it needs to be optimized for deflection, I don't want to use the 16x26. I want to modify it myself. I don't want to go, and sometimes you could go down, right? You could use a smaller size rather than, because it's more optimal. Maybe you don't want to do that. Maybe it's going to take it all the way down to an 8x10 and you say, no, I don't ever want to use an 8x10. I'm going to leave it as my 8x21 or something like that. So you can kind of really change and tweak exactly how these suggested shapes are used. And these suggested shapes are obviously, again, based on the design list that you've chosen, right? So in this case, I was designing based on all the single angles, and so it's looking through the single angle spreadsheet to find that member that's going to work. Now let's go ahead and look also at joint reactions. So if we look at our reactions, now this is what we're going to take over into RISA Foundation to design, our foundations. This is the information both in the X and the Y and the Z direction and those moments that's going to be taken over to RISA Foundation. And we'll see that a little bit later in one of our other videos. In one of our other classes that Francisco is going to go through and see exactly how we take these reactions into RISA Foundation and then use this information from RISA-3D and RISA Floor based on that load information to design those foundations. But in this case, we can look at this again. We can go ahead and look at our regular reactions and see them, sort them, and kind of see, hey, do we have any really big issues that I would be concerned about? Before we go any further, though, and this kind of leads us into a little bit of what I'll talk about next when we look at RISA connection, we may want to set up some seismic detailing, right? And so that's another one of the really nice features of RISA-3D here is I can go ahead and look at our seismic design rules to start. And so for columns, beams, braces, for concrete walls, we can set up different levels of our seismic design rules. So for instance, for a column here, right, we've got our ordinary, concentric, like braced frame. We've got different beam things here. But really what we want to look at in this case, I want to look at braces, right? I want to set my braces in a certain way. And so here we can see, for an ordinary frame, are we requiring overstrength? Are we doing a Taylor-Ovar check? This is all from AISC 341. And so that's what we're going to use when we do this check. And so the first thing I want to do, though, is I want to set that rule. I want to set those braced rules to our brace frames. And so I'm going to go ahead and turn off kind of the labeling of the unity check. And I'm going to go ahead and use kind of this select based on criteria to select all of our braces. So I want to choose our member type and our vertical braces, click apply here. So I've got all our braces selected. And then I'm going to go ahead and, I'm going to lose results, and that's okay. I'm going to modify the properties here. And when I modify the property here, I want to change our seismic rule. So really, I'm going to modify the design here. And so I'm going to set my seismic rule in this case to be an ordinary brace frame. So I'm going to click on the Use tab here, set that. We're going to apply this to all selected members and click Apply. Now we could go ahead and actually see this. So if we look at our seismic rules here, we can see, hey, all of our braces now have that seismic rule apply. So we can see very easily, very visually exactly what we've done here. So now we're going to go ahead and rerun the model again. So I'm going to rerun that same batch solution. So click OK. And so obviously these design rules are important if you're designing seismically detailed connections as well, like I mentioned before. And so now, although we are including the AISC 341 code, RISA lets us know that the design is either adequate or not adequate, rather than really trying to optimize for seismic provisions. Therefore, we may need to use a different shape, for instance. We may need to see that, maybe an angle is not going to work in this case, and maybe we need to use a tube or something else. And so we're going to go ahead and do that to be able to obtain a passing result. Now, again, these requirements do not change the design output that we've got through AISC 360, right? That's your kind of standard steel code check. This is really, and code design and optimization, this is really an additional code check based on if you want to do seismic detailing or not. So once the analysis is finished, we can go ahead and open up our seismic detailing spreadsheet. And here, pretty plain to see, we're seeing our passing based on this required compression and tension, but really where we're seeing the failure is here in our slenderness checks. And so that's where maybe we need to consider using a member, because we're doing that KL over R check, maybe we need to consider using a member that's has some different slenderness ratios than the angles here. And if we want to look at that in detail, I'm going to just go ahead and select the first one, and I'm going to choose to open up our detailed report. And so in looking at the detailed report, obviously we pass in our kind of standard bending check and our standard AISC 360 check, because what's happening for the seismic check is not changing that. But if we come down here, now we have our envelope seismic detailing results based on AISC 341. And we can see here that our KL over R at 196 is much greater than our 113, which is required based on F1.5B. And so now we've got to make a choice. Can we update this? Can we use bigger angle shapes in order to make this work? Or maybe does it make sense to choose a different type of shape? And so in this case, that's what I'm going to do. I'm going to choose a different type of shape. So I'm going to change our section set here. I'm going to change it from an angle, and let's change it into a tube. So I'm going to choose a tube here, and I'm actually going to choose an A1085 tube. So for those of you who aren't familiar with A1085, we can talk about that for just a second. And so before I go ahead and do that, let's choose HSS 10 by 10 by, let's choose 10 by 10 by 10, A1085, click OK. Let's change our design list here. So we're doing a square tube, so let's use a square tube A1085, and we also need to change our material to A1085. And so if we go ahead then and rerun this, so batch solution again, rerun it. Now the A1085, so the question is, maybe some of you are familiar with it, maybe you're not familiar with it, maybe you're using it, maybe you're not. So what's the difference between A1085 and your A500? So the first thing is that A1085 is a 50 KSI yield stress. So you've got a higher yield stress than the 42 or 46 that you're finding with A500. Also, really the biggest thing is that we've got a tighter wall tolerance in kind of rolling and fabrication of these shapes. So you no longer need to use that reduction of wall thickness, that 0.93 that the code requires you, because there's this tighter tolerance in making the members. And so that gives you, ultimately, that gives you more strength, right? You can use that full thickness instead of using that reduction in thickness. So if you need more information, the Steel Tube Institute the STI is a great resource for that. And also most of the manufacturers, most of the really big manufacturers in the country are rolling A1085 tubes. And so you're not gonna have a problem finding them. So they're not kind of few and far between. You're gonna be able to use them kind of when you want. So now that we went ahead and did that, let's go ahead back and use our seismic detailing here. Now we're seeing our slenderness checks are indeed passing. We can go ahead and look at one of these detailed reports. So looking at the detailed report, we can see obviously the bending is much smaller because we just have a much bigger shape, more area, more going on here. But obviously now we're also passing in our slenderness check. So where we're required, where we have 79.772, we have obviously something greater than that as our allowable here, 96.333. And so we're no longer having any issues in our seismic detailing. Now, before we go ahead and we move on into RISA connection, the last thing I want to do is I want to show a little bit about the report creation in RISA-3D. And so if I come up here to click on print, we're going to choose to print a report instead. And so we can choose to kind of create the information of our report. So many of you may be familiar with the report creation features here. And so the first thing is we can always include, one of the things I love about this is we can always include additional items. For instance, if we wanted to bring in, say, an elevation, or if we wanted to bring in a a composite beam report from RISA floor. We could do that. When we finish our RISA connection stuff, if we wanted to bring in our RISA connection stuff into here, we could do that. Maybe we have details, their PDFs or their hand drawings or sketches or something. We wanted to include that. Any of that stuff can be included just by clicking this Add Images and Documents. And so we can go ahead and choose, hey, this is what I want to add. Maybe I want to add something from my connection report or something like that. So we can go ahead and add really anything that we want. Additionally, we go ahead and just either drag or drop or click the add button to add in various different kind of report sections. So if I choose hot rolled here, I just add the hot rolled section, maybe the section sets, I want to include that too. Maybe I want to come down in here to my loads or my results. So member deflections or something like that, maybe it's our beam checks, so we can include all of this information. And then one of the really nice things about this is we can actually save a template. So many times you're going to do a steel model or steel design and you're going to say, hey, I have a specific way in which I want to look at my results. And I want to look at my results the same way. I want to include the materials and the section sets and the deflections and the loads and the unity checks and the reactions. And that's what I need to either apply to my report and then give that to a reviewer or give that to a code official or something, or it just needs to be documented for our particular project. You can go ahead and save that as a report name or as a template so that you can use that each and every time. So you don't have to set up the report every time that you use it from scratch. And so that's really a great feature. And then once you're ready, we can go ahead and just say create PDF, right? So I'm going to create a PDF file. I'd save it. So in this case, I'll just save this as my RISA-3D report. It's just going to write my file. And then for me, I'm using Bluebeam. It's just going to launch my Bluebeam. And then we see here, okay, here's kind of everything that I chose and all the different tables. And if I had different images and stuff like that, it would include that as well. Thank you for viewing this session of the RISA Steel Building Workshop focused on RISA-3D. When you're ready, please proceed to the next video, which focuses on RISA connection.